Welcome to Unit 8, Lesson 4, the natural exponential function. We have something called the natural number, or E, Euler's number, and it's approximately equal to 2.71828. You should have an E button on your calculator somewhere. It might be in your second function area. You just need to look and find it. So the function f of x is equal to e to the power of x is called the natural exponential function. And it involves Euler's number, which we just talked about. Now, everything that we've talked about in this unit, nothing's changed. It's just that your base number has changed. So 2.71828 is your base, and you're going to just figure out your problems from there. So this is a basic graph of e to the power of x. And the graph will look like this. So you'll have a point at 0, 1, and then your next point will be at 1, 2.718, etc. You're just changing that x value to give you your next coordinates. It's just an increasing exponential function. So it has these properties for this function. The domain is an element of the reals. The range, we have that horizontal asymptote at y equals 0, so y is greater than 0. It's an increasing function. It opens upwards. The function is 1-to-1 ratio, so if e to the x is equal to e to the x2, then x1 equals x2. And then you can see here the value 0 is less than e to the power of x is less than 1 for x when x is less than 0. And e to the x is greater than 1 for x is greater than 0. So on this side of the y-axis, the numbers will be fractions. And on this side of the y-axis, they will be 1 or greater. You haven't seen this term yet. It's LN stands for natural log. The logarithms is the next unit, unit 9. So we'll talk about that in the next unit, but e to the power of natural log of x is equal to x. And f of f to the minus 1 of x is equal to x, and that makes sense. The function of the inverse of the function is x. So we'll cover this in the next unit coming up, so don't worry about that too much, but it is one of the properties of the graph. And then, as we discussed before, the horizontal asymptote. On the back here, there's just 3 examples of what this graph looks like, and note to the fact that we can still do transformations and translations to the graph. So I've drawn the 3 graphs for you. E to the power of x minus 2, that's just the base e to the x graph with a vertical shift. This is your k value down 2 units. So notice that the horizontal asymptote moves down to y equals minus 2. And then the graph is exactly the same as it was, just shifted down 2 units. In B, we have y is equal to negative e to the power of negative x. So we have a flip over the x-axis, and then notice that the shape of the graph has changed slightly to change directions. And then the final example, y is equal to the absolute value of e to the x minus 1. So you're going to draw your base function e to the power of x and then shift it down 1 unit. So if you had your base function, the y-intercept now goes through 0 instead of 0, 1. You're finding the absolute value of this function. So if you shifted the graph down and the horizontal asymptote was then at negative 1 down here, then you're going to take all those, sorry, I'm just going to draw it in. Now, your base function without the absolute value, it's going to look something like this. And it will just carry off, continuing on that graph. So don't forget, when we find the absolute value of something, we're taking all the negative y values and making them positive. So from here, 0, 0, we're just flipping all these coordinates onto the positive y-axis. And there's no practice questions in this section, but you can just move on to the homework for this unit.